In the previous lecture in section 1.5, you learned how to find solutions of homogeneous linear systems, the types of solutions that existed for those solutions, and then how to interpret those solutions geometrically. In the next set of slides, we are going to look at a non-homogeneous linear system and how the solution compares to that of the homogeneous case. So remember, homogeneous simply means that the right-hand side are zeros. So notice here that I have written the augmented matrix for the linear system, but in this case I have included the constant column, which has the zeros. Note that you don't really need to put that in because that column will never change no matter what type of elementary row operation you perform on the system. So let's just look at it in terms of the coefficient matrix. Once the coefficient matrix is in reduced form, we have the following. Right? So this is in reduced row echelon form. So we see that x2 is a free variable and x1 can be written in terms of x2. So then we simply solve for x1 as a function of x2, and now we can write the solution, which is x equal to x1, x2. And now I'm going to replace x1 with its corresponding representation in terms of x2, which we see here. Then we find that the solution is simply a constant multiple of the vector 1, 2. So x2 is free, so it can take on any value. So again, the solution is just a constant multiple of the vector 1/2, 1. Another way to write that, of course, is to say the span of 1/2, 1. So now let's recall what geometrically the solution to this homogeneous linear system looks like. Again, we said that the solution was the span of the vector 1/2, 1, which is exactly the same as any constant multiple of the vector 1/2, 1. In this case, x2 is just any real number. So, for example, if I took x2 and made it equal to 2, then the vector 2 times 1/2, 1, which is 1, 2, is also an element of the span. So if we were to graph 1, 2, the vector 1, 2, then we would get the following vector. Likewise, if I again just change the value of x2, let's say that x2 is -1, then we have -1 times the vector 1/2, 1, which gives us -1/2, -1. So that's also part of the span. And so if we were to graph that vector, it would look something like this. So notice that any vector that is in the span of this single vector 1/2, 1 lies on the same line that goes through 1/2, 1. So now let's look at the solution of the non-homogeneous case and compare it to that of the homogeneous case. For the non-homogeneous case, we have the same coefficient matrix, so the left-hand side of the linear system is the same. The only difference is that the constant quantities are not 0, 0. So here I've taken this linear system and written the augmented matrix for the linear system. And if we were to put that into reduced row echelon form, we get the following. Notice that the coefficient part is exactly the same as we had in the previous example. So the only difference is what is in the constant column. Let's see how we write this solution in parametric form. So again, we know that the quantity x2 is free. All right, so we want to say that x2 is free. x1, so I'm just now interpreting the first line of the augmented matrix. We have x1 minus 1/2 x2 is equal to -1. Right, so now we're going to write x1 in terms of x2. So we have x1 is equal to -1 plus 1/2 x2. So now we want to write the solution in parametric form. So again, we have the vector x containing quantities x1 and x2, And now we're going to replace x1 with the way it is written in terms of x2, which is minus 1 plus 1/2 x2. And of course, x2 is just a free parameter, so we'll leave it in the vector unchanged. So I'm going to write this just a little bit differently, and that is that has a constant part, which is -1, plus a part that is some multiple of the quantity x2, but so does the second line. The constant part, however, is 0, and then we have 1 x2. So now I can separate this solution into the sum of two vectors, the vector -1, 0, and the vector x2 times 1/2 1, which looks a lot like our homogeneous solution. Notice that the solution to the non-homogeneous linear system has two parts. One part, as I mentioned before, looks familiar. It looks like the solution to the homogeneous linear system. We're going to call this xh, or vector xh. The second part doesn't have any arbitrary parameter associated with it. It is called the particular solution, and we're going to label it as xp. So this is the particular part. So the solution to the non-homogeneous equation is always going to be some vector xp, which represents the particular solution, plus the homogeneous solution. So here I've drawn the solution to the homogeneous linear system, which we recall is just a line that goes through the vector 1/2 1 and passes through the origin. So now on this same graph, let's draw the solution to the non-homogeneous case. So that contains two parts. It contains the homogeneous solution plus a particular solution, which is the vector 1, 0. Well, let's consider, again, x2 is any real number, so let's just make x2 equal to 1. If x2 is equal to 1, then the non-homogeneous solution is going to be 1/2 1 plus the vector 1, 0. So what does that say? To draw that geometrically, if we want to take the sum of two vectors, we simply place the vector 1, 0. So here is that vector right here, 1, 0. And we're going to place it at the tip of the homogeneous solution, right? We're going to take their sum. So it looks something like that. And we would do that for every solution from the homogeneous case. We would simply add the vector 1, 0 to the tip of it. Notice that what that does is it gives us a new solution, which again is just a line. But this line, which you notice is parallel to the homogeneous solution, is translated to the tip of the vector 1, 0, which we see here. So again, for the non-homogeneous case, we simply add the vector 1, 0 to every vector of the homogeneous solution. And what that ends up doing is simply translating the line over to the tip of the vector 1, 0. So the non-homogeneous solution is the homogeneous solution simply translated to the tip of the particular vector, which is xp. So now we see both solutions together, the homogeneous solution, which you see the line in black, and the non-homogeneous solution, which is the line in green, are both parallel to each other. And in fact, the non-homogeneous solution is a solution that is parallel to the homogeneous solution and is simply translated to the tip of the particular vector. So in conclusion, the homogeneous solution and the non-homogeneous solutions are related in the following way. The non-homogeneous solution is the homogeneous solution plus a particular solution, which here we're calling P or XP. And XH, of course, is the solution to the homogeneous part, and P is the particular part. The solutions are parallel, and the non-homogeneous solution is simply a translation of the homogeneous solution to the tip of XP.